This PhysCast will look at a solution to a wave equation, in this case the classical wave equation. Pause the video and read carefully through the question. Now that you've read the question, you'll see that there's a proposed solution here, a function of position and time, that's claimed to be a solution to the classical wave equation. And we need to show that that is in fact the case, and then find an expression for the speed of the wave. So let's begin by remembering what the classical wave equation is. The classical wave equation says that if you take the second spatial derivative of that function, it should equal some quantity that we write as 1 over v squared multiplied by the second time derivative of that function. So the important points are those two second derivatives, the one with respect to position and the one with respect to time, should be equal to each other multiplied by some constant in there, importantly some positive constant that we can identify with the speed of the wave. So we can begin with our proposed solution by calculating, for example, the first spatial derivative. Now this is a sine function here, so the first spatial derivative will involve the derivative with respect to x of whatever's inside the sine argument here. That's just going to be the derivative of kx, which, if k is a constant, of course, is just going to be k multiplied by the constant a, and then our sine function will become a cosine function of exactly the same argument, kx minus omega t minus phi. And then we can find our second spatial derivative by taking the derivative of that expression there, where once again we'll take the derivative with respect to x of what's inside the cosine function here, which once again will be a factor of k, so that k will also multiply with the original factor there to give us k squared. The a will stay the same. Our cosine function will become minus sine. So let's put a minus sign there, and then sine of kx minus omega t minus phi. And what you'll see there is this expression here. This should be probably familiar to you. That is just our original function. So we could write this here as minus k squared times our original function y. Now we can do essentially the same kind of process, but now with our time derivative. So our first time derivative here, again we'll take the time derivative of whatever's inside the sine function, and that's going to be minus omega multiplied by this constant a, and our sine function becomes a cosine function, again of the same argument, kx minus omega t minus phi. And our second time derivative here, taking the time derivative of that first derivative, we once again pick up a factor of minus omega. So minus omega times omega gives me omega squared times a, and my cosine becomes again a minus sine of kx minus omega t minus phi, which again, as we saw before, can be written here as minus omega squared times y. So this shows from this first one, for example, I can write that this function y has the property that it equals minus 1 over k squared of this second derivative. That's one of the properties that it has. Another property that we've just shown here is I can also write that function y as minus 1 over omega squared of the second time derivative. Of course, these functions are the same, so I can put these two functions together. This expression here for y must be equal to that one, so I can write here that minus 1 over k squared d2y by dx squared must equal minus 1 over omega squared d2y by dt squared. And rearranging that, if you like multiplying both sides by minus k squared, I'll simply get that d2y by dx squared equals k squared over omega squared of d2y by dt squared. And that is indeed exactly what I wanted my classical wave equation to be, that my second spatial derivative equals some positive quantity here, k squared divided by omega squared, times my second time derivative. So that does indeed show that this sinusoidal travelling wave that we were given at the start of our question is indeed a solution to the classical wave equation. And then, fairly straightforwardly, I can identify that this quantity in here must be equal to what we've called 1 over the square of the speed. Must be k squared over omega squared, which allows me to straightforwardly identify that the speed of this wave must equal omega divided by k, which is probably a relationship you've seen before. But this way of not exactly solving the differential equation we've got here, but demonstrating that a given solution does in fact solve it by essentially equating the left and right hand sides and seeing if that requires any particular relationships between some of the quantities involved, is a very useful technique, and one that's used not just for classical wave equations but quite often for solutions, for example, to the Schrödinger equation.